Hello everyone, my name is Ganiming. Today I am presenting my contribution to our computer organization and architecture group project alongside with my team members, which is Su Niao Ming, Braden Lee Ting Fong, and Tiu Jie Hong. For this performance benchmark analysis, I took on the role of hardware optimization engineer. My assigned tool is HWINFO64, a comprehensive hardware monitoring utility. I'll be demonstrating how I installed, configured, and utilized this tool on my computer, which features an AMD Ryzen 7 7445HS processor to extract microarchitectural telemetry and evaluate hardware bottlenecks. So now let's begin with how to operate HWINFO64. Unlike synthetic workload generators, HWINFO64 is a passive diagnostic tool. This means it doesn't stress the hardware itself. Instead, it reads the telemetry directly from the motherboard sensors. So to start, I launch the application and immediately select the sensors only mode. So I will start with HWINFO64. And then I start with sensors only mode. And then I click start. So this bypasses the general system summary and takes us straight to the live data stream. So close the update. And then here we go is the HW64 interface. As you can see, the interface presents a massive volume of real-time metrics, everything from the voltages and active clock rates to individual core temperature. Because it is nearly impossible to track all of this live during a 30-minute stress test, so the most critical feature to use this data is the data logger. So by clicking the logging start, so I can export all the readings into a CSV file. So let me write a title with workload A, log, and then I click save. So it will start logging the data into CSV file. So to actually execute the performance benchmark, I must pair with the active workload generator. So I use SynBench R23 and configuring it to run a 30-minute multi-core loop for workload A and a 10-minute single core loop for workload B, while HWINFO64 silently log the hardware reaction in the background. So here we can see the SynBench R23 app. For workload A, I will click Advanced Benchmark, and then I will choose 30 minutes to test stability, and then I click start. So the time will start running, and then we wait for 30 minutes. So now after 30 minutes, I will press the logging stop button. Do the same thing for workload 2 by pressing start button on CPU single core. So now I will demonstrate how I obtain the required COA metrics for workload A, which tests the core pipeline processing throughput and thermodynamics. So after running the 30 minutes multi-core loop, I open the exported CSV log, which is this I opened in Excel. To find our system bottlenecks, I isolated three specific metrics. First is the peak package power, which is column DY, and then core clocks, which is column S, and then the CPU temperature, which is column DD. So if we look at the data here, we can see all 16 execution threads of the Ryzen 7 processor were fully saturated with instructions. The CPU package power spiked to a max of 30 and something watts. So we will try to get the data. The CPU package power has spiked to the maximum of 35.437 watts, which is the highest within this data. So here I type max for the column DD, and I start from row 2 until row 903. So I get a value of 100.4, which is the peak value of the temperature. So we can see right there in the log that the hardware thermal protection mechanism engaged. The maximum boost clock, which we can get here. So I get the value from the maximum for row 2 until row 903, and then I get the value of 3,809. So in this column, I will write min
of row 2, S2 until S903. So the value of 2920.6 is the value where the boost clock download by the system to prevent silicon degradation. So that's all for the extracting metrics for workload A. So now moving on to the workload B, we shift our focus to advanced architectural behaviors, specifically observing how the operating system handles a dense single-threaded workload. So we can see that the core 4 has heavily utilized by the single-threaded SynBatch task. You can see its utility was at 103.6%, and the temperature has reached until 85 degrees Celsius. However, to prevent core 4 from continuing to heat up and creating a localized thermal hotspot, the Windows scheduler dynamically migrated the workload. In this same second, we can see the core 0 utility spikes to 99.3% to take over the processing load, driving its individual temperature up to 65.7 degrees Celsius. By highlighting these specific rows in the log, we have proved that the dynamic thread migration, the operating system actively bounces the heavy instruction string between physical cores to balance the thermal density across the entire AMD Ryzen die, allowing it to maintain maximum boost clocks. That's all for the extracting metrics for workload B. To conclude with the analysis and discussion of these metrics, workload A clearly illustrates the architectural concept of thermal throttling and pipeline saturation. When the processor was pushed to its limit, it resulted in a clock frequency delta, or data tau, with a value of 888.4 MHz. This massive performance penalty proved that regardless of how efficient a superscalar execution engine is, sustained throughput is ultimately bounded by the physical thermal constraints. For workload B, our metric successfully met the concept of dynamic thread migration. If the operating system left the heavy single-threaded rendering task and core to just core 4, it would have rapidly created a severe localized thermal hotspot, eventually hitting the 100 degrees Celsius limit we saw in the workload A. By bouncing the workload between different physical cores, the operating system balances the thermal density across the entire CPU die, allowing the architecture to sustain its maximum boost clocks for much longer. Ultimately, using HW Info 64 provided incredible granular visibility into these micro-architectural behaviors. Top, its main limitation is that it requires a secondary program to actually generate the workloads. Thank you for watching my demonstration.